It's my pleasure to introduce Theo Johnson-Freyd, who's going to talk to us about super vertex operator algebras and some exceptional finite groups.
So thank you all for coming to my talk. I think it's traditional to thank the organizers for the invitation, but instead I should probably apologize because I think you invited me to talk about some like important theorem in, maybe having some structure in higher categories or something like that. And instead, I'm going to use this as an opportunity to tell you about a theorem that probably is not important. I doubt that so I wrote up the theorem, you can read it, but I'll spend some time explaining the words, but I doubt that it actually has any kind of nobody's ever going to cite it or anything. Like it's just sort of but it was a really fun project. And so I want to tell you about why this type of project is fun and why you should do it occasionally, but don't make it your career because then you wouldn't get cited. So, so as I said, I'll say a bit about the words in the statement of the theorem in a moment, but I want to give some really what I want to do is tell you why I wanted to do this classification and why I kind of noticed it and discovered it. And so that's what I'm going to spend my time doing. So in exceptional group theory, so you look at the classification of finite simple groups, and the classification of finite simple groups goes something like the following. There's a bunch of infinite families, and then some sporadic groups. And the word sporadic just means it's not part of an infinite family. And so now you can ask, where do these groups why are they? So the infinite families, the answer is all that they all exist because of Lie theory. So this is all kind of somehow finite Lie theory. There's you might take the orthogonal group in some positive character over some finite field, and that'll be some essentially simple group. Maybe you have to kill some center or something like that. But they exist because of Lie groups and because of classical representation theory, essentially. Even from the perspective of finite simple groups, even the F2 points of E8 is still essentially a classical object. It still exists for kind of linear algebraic reasons. Because honestly, to write down the Lie group E8 isn't that hard. I mean, compared to some of the finite groups, you can just you write down a Dynkin diagram and you prove some general theorem that says that Dynkin diagrams give you groups. Maybe you even give some general construction, maybe from lattice theory or vertex operator algebra theory. And you can get all these groups. So one of the main questions you might ask is kind of why are these? Why are in the sense of kind of why do they exist? Why are they? And this is not the type of question that can have an answer, really. I mean, we can't have a precise answer, but it can have kind of vague answers. And so you have sort of various possibilities. So sometimes the answer is just really disappointing. So and maybe that's what you should. Maybe you're a pessimist, and maybe you think that for no reason. I mean, for example, something like the third Yanko group. Nobody knows what it is doing. It doesn't have any reasonable representations. I mean, yes, every group you can write down as the symmetries of something in some stupid way. But to write down the Yanko group, as far as anybody knows, as the symmetries of something, you basically have to put all of the Yanko group into that thing. And so you haven't learned anything. The Yanko group exists because it happens that you might be able to form some extension of something and then stick something else in some specific way. And Yanko found it by just looking and saying, oh, well, I can't rule out the possibility that there's a simple group with an order 2 element whose centralizer has this structure. Maybe I'll go and try to build a simple group with centralizer with that structure. And that's all that exists. So and as far as anybody knows, that's the end of the story on Yanko's third group. Yanko, by the way, was the reason that we have exceptional groups. So by the sort of early 20th century, essentially all the infinite families had been found by people like Chevalier. And then there were the Mathieu groups that had been found in the late 19th century. And it was really reasonable to think that was the full list of finite simple groups. And then Yanko found one in the 40s, Yanko first. And then the very last sporadic group ever found was Yanko 4. So Yanko kind of gets both ends of it. Okay, so that's one possible reason. The most common phenomenon in the theory of sporadic groups is that maybe the group is the symmetries of something combinatorial, maybe, something sort of interesting, but complicated. Like maybe there's some beautiful, rich combinatorial object that happens to exist for some kind of, maybe there's some coincidence that causes the exceptional object to exist. Like it happens that it happens that 6 is 5 plus 1, and that means that you can put A5. How does that work? So it happens that 6 is 5 plus 1, and that means that like that SL25 has a 6-dimensional permutation representation on the projective line, but then there's not that many possible groups, and so it happens that it's also A5, and then you sort of build a coincidence from that. Or you use the fact that S6 happens to have an outer automorphism and none of the other symmetric groups do, and you build something with that. So that's the sort of some interesting but complicated thing, and maybe a good example of that. Is the Higman-Sims group. Maybe this is the best example, which is the automorphism group of some particular graph, some particular graph called the Higman-Sims graph on like 100 vertices. Every vertex has valence 22, and it's hard to write down this graph. I mean, I wouldn't be able to recite it live, but it's a lot less hard to write down this graph than to say write down some presentation of the. And then there's a few groups that are a few groups in the sporadic family that seem to be like really fundamental. And that's the one I want to talk most about. So maybe I think this is the typical situation for the sporadic groups, at least as far as people know. But there's a few groups that are like, as I said, that are really fundamental, that exist for some really good reason. And right now, I would say the group that we understand the best and really understand why it's so fundamental in the sporadic family is Conway's largest sporadic group. And Conway's largest sporadic group, so Conway first found it Conway was very good at seeing where a good problem would be that didn't look like it should be a good problem. And he first found it by calculating sort of the usual definition is you take it, it feels like it's of this class, where it feels like it's sort of the automorphism of some particular but complicated object. So he found it by looking at the automorphisms of the Leech lattice. And I don't really want the automorphisms because this has a center just given by there's some scalars that act on any lattice, so I should take the projective automorphisms of the Leech lattice. Like I should just kill the center. And this doesn't make it look particularly sort of really important. But what Conway figured out, so this is Conway's largest group, simple group. And what Conway figured out is that actually this group is much, much more fundamental. It's much, much more sort of part of the like essential building blocks of nature than it looks like. So an example of it being part of the essential building blocks of nature is the following. Actually, this thing on Leech lattice is totally a red herring. Really what this group is, according to Conway, is that, or maybe Conway and Sloan, I forget. But really what this group is, as I said, I don't remember who probably Sloan. Let's give Sloan some credit because at least where this would be found is in their joint work. So really what this group is the following. You take the unique, so this is some complicated lattice. Like it's not too bad. You can write it down in a few paragraphs, but still not that easy. But what you really could do is you could take the unique lattice of signature 25,1. So this is some complicated lattice inside of R24. This is some specific, so it turns out for any indefinite signature, where the difference of the signature, so this is like living inside of Minkowski space with 25 spatial directions and one time direction. And you take for any indefinite signature, there's a unique lattice, even unimodular lattice of that signature. So this is the unique, even unimodular lattice in R25,1. So you take that thing, And you did the following. Something you can do with any lattice at all is the following. You can take the automorphism group of that lattice. That's some big, this is like, so this has some indefinite signature. So this is some integer form of the orthogonal group with signature 25, 1. And then among the automorphisms, there's some Weyl group. There's sort of the automorphisms generated by reflections against vectors of length, against roots. So this is sort of the subgroup generated by reflections. By reflections against simple roots. There's infinitely many simple roots because it has indefinite signature, but you can still build this subgroup. So this is what you might think of as like the outer automorphisms, the automorphisms of the Dynkin diagram. If this were the root lattice of a Lie group, this would be the automorphism of the Dynkin diagram. And what Conway shows, or Conway and Sloan, is that this group is Conway 1. So there's a reason to care. All of a sudden you perk up and it's like, oh, wow, this is some basic object in kind of Lie theory. So that's not what I'm going to talk about. I just thought I'd mention it. So what am I really going to talk about? I want to tell you about yet a third way that this group. So these two are sort of related. I mean, in fact, you prove one of these by proving the other. I guess you prove this one by getting it back down to the Leech lattice case. And it turns out what's sort of secretly hidden here is that this even unimodular lattice, which would have existed with any value of 25, as long as 25 is one more than a multiple of 8, you could build a lattice like this. But for this specific value of 25, somehow this lattice has the Leech lattice living inside in a sort of essential way. It knows about the Leech lattice. So what's really going on, what seems to be going on is, but this is, I don't think there's a precise theorem of this form. What seems to be going on is that when you look at things like lattices and dimensions less than about 25, the structure is pretty finite. In low dimensions lattices, there's not very many lattices. It's a very, very rigid problem. And then there's some sort of phase transition that occurs right around this dimension. And when you do sort of lattice theory in high dimensions, there's just like bajillions of lattices. And nobody knows anything. Like we don't have any, like in the positive, I mean, in the split signature case, we know there's like unique unimodular even lattices, but in the positive definite case, nobody has a clue how to do dense lattice packings or anything like that in high dimension. And this is right at this sort of phase transition. And I think that's what's going on. So what I wanted to tell you about was a third way that this group shows up, which as far as I know is unrelated to these. So there's a third way this shows up, which is a theorem this is the theorem that John Duncan proves in his PhD thesis. And what Duncan shows is the following: is that there's yet another, as I said, yet another thing whose automorphisms is CO1. That CO1 is the automorphism group of the holomorphic n equals 1 SVOA with no free fermions, with a minimal central charge. The minimal central charge holomorphic. So he shows that this thing is unique. So the minimal central charge n equals 1 SVOA with no free fermions. So C, it turns out to be 12. But anyway, it's the smallest central charge you can do and have a holomorphic n equals 1 SVOA without free fermions. And this is supposed to be, well, this is like essentially a kind of the reason why this is an interesting, one of the reasons why this is an interesting theorem is that it's been long believed but not yet known. So it's kind of still a conjecture by that, for instance, the monster group sort of famously should be the automorphism group of the kind of minimal central charge holomorphic bosonic VOA. So not super with no free bosons. And this conjecture is almost known. I mean, very famously, we know what the minimal central charge boson holomorphic VOA is supposed to be. I mean, it's supposed to be the monster module, and it's known that its automorphisms is the monster group. The only question is this word the. So it's not known to be unique, whereas in the sort of in the Conway case, it is known to be unique. And the reason is because like there's just more control over this case. We have sort of better access. It's lower central charge, and in particular, although there's no free fermions in this theory, there are free bosons. That gives you a lot of control over the object. Okay, great. So that was about to be what I'm about to say.
Could you repeat the question?
What does n equal 1 indicate?
Sorry.
You're supposed to be commentating.
Everybody for Zoom.
Yeah. So my question was, what does n equals 1 indicate? And Theo will explain.
Right. So great. So I'm not going to say what a VOA is because I probably wouldn't be able to recite the definition on the spot anyway. But I will say some of these words, and I probably should. I've left out words like sort of. There's all sorts of niceness conditions that I'm leaving out that are like, maybe I want unitary vertex algebras or something like that. And basically, when you do classification theorems like this, I should have put some niceness conditions in for this. And you just pick any niceness condition that lets you get off the ground, and then you do a classification, and then you prove from the classification that you have all niceness conditions you could ever want. And then it didn't matter which niceness condition you put in to get off the ground. So pick your favorite niceness condition, and then the theorem is true. Okay, so let me start saying what some of these words mean, and then I'll tell you how it connects to my classification. So let's see, what did I want to say first? So I guess I should start with what is an n equals 1 structure on a VOA. So suppose you have a vertex, so a super vertex operator algebra. So I guess this is a definition. If V is maybe I should call it sort of n equals 0, a thing without supersymmetry. So n always counts how many supersymmetry generators you have. So if you have just a plain as sort of super vertex operator algebra, so a vertex operator algebra in super vector spaces, and maybe I think I'm going to write, maybe I'll write kind of the conformal vector. I just need a name for it. Maybe I call it, I think Katz calls it nu, and so that's what I'm going to call it. Then an n equals 1 structure, an n equals 1 structure is a choice of super conformal vector. So these words mean the same thing. Maybe I call it tau, and the axioms for tau are that tau should be a Virasoro primary. So it should have spin 3 halves under the conformal structure, and maybe that'll follow from the other thing I'm about to write. But more importantly is the OP of tau itself. So maybe this is a VOA of central charge C, and then I could get like 2/3 C divided by. So there's a pole of order 3 with that's 2/3 C, and then just you pick up the conformal vector. So that's what it is. So what you're supposed to think is the following. You're supposed to think that, well, you could think lots of things. One thing you could think is you could think of tau as being like, you could think of a VOA as something like a graded vector space, where you think of sort of the conformal structures giving you like the grading. And maybe that's not quite the right way to think, but anyway, you can think of it as some sort of graded vector space, but you should think of tau as being something like, in general, the way you should think about supersymmetries is you should think of the supersymmetry generator as being something like a differential on your vector space. And it's not quite squaring to 0. That would this is like tau squared morally. And it's not quite squaring to 0, but it's squaring to something which is, so it's like maybe like a curved differential. And in general, if you are in any dimension, that's how you should think about supersymmetry. It's like a choice of something whose curvature is the energy function, is the stress energy function. So this is something like the stress energy tensor. So that's what there, I answered Chris's question. So okay, so that was the first thing I needed to tell you. So I kind of don't want to erase my theorem yet. So I think I'm stuck on this side of the board. So holomorphic, I won't even, so I used the word holomorphic twice. Holomorphic, I'll just remind that for me, this means that the category of representations is just the category of vector spaces, except I'm super, and so I really mean super vector spaces. But basically, the only representation, the only reducible local representation is the vacuum representation itself. So the most, maybe the most famous example of the 8 at level 1 has this property. Oh, and I'm erasing it right now, but I have this sort of no-free fermions that I put both places and no-free bosons. So let me sort of say why I want to rule those out. So, so what is going on with these things? So of course, a free kind of fermion or boson, these are just of course the fields in your vertex algebra of spin either a half or 1 for the two cases. And why I rule them out is the following. So kind of, I think something probably people know, or at least some people know very well in this audience, is that in any vertex algebra, the free bosons, these form a Lie algebra. And this Lie algebra acts on the whole vertex algebra. So it maps to the Lie algebra of the automorphism group of your vertex algebra. And this map is an iso. It's an iso if your vertex algebra is, say, rational. You always have a map that's an iso if you're rational. In particular, it's an iso if you're holomorphic. And I didn't actually put rationality into my theorem, but it follows very quickly from the other conditions, so that's okay. So that's true for any vertex algebra if you sort of want where automorphisms mean, say, preserving just the conformal vector. But if you want to do automorphisms to preserve the superconformal vector, it's essentially the same statement. If you care about the automorphisms that preserve, maybe I'll call it like the n equals 1 automorphisms. So this is the automorphisms preserving tau. Then the same statement is true, that there's always a map which is an iso if phi is rational from the free fermions. And the free fermions are always naturally a Lie algebra in any super conformal field theory. So by ruling out free fermions, all I'm doing is I'm really focusing attention. So this just gets me into the world. This is like makes it a really interesting problem. It focuses attention on finite groups. Otherwise, you'd have some big Lie group of symmetries, and it'll sort of swamp out any interesting finite group theory, probably. That's all that's doing. So now, what did I actually want to tell you? Okay, so now I think I've given I should have to tell you what a simply connected WZW algebra is. A simply connected WZW algebra, that for me means, this just means, so V even meaning the even half of my vertex algebra, and this just means that this is any VOA generated by its free bosons. And maybe I want like unitary, thing like that. Nice, whatever nice means for you. Maybe if I don't put some words in, then I should distinguish between WZW and Kac-Moody algebras. But for me, it means a nice VOA generated by its free bosons, and I don't find Kac-Moody algebras nice, so I reject them and won't say more about them. So it means it's generated by its free bosons. So the point is that right. So what's the point? So the point is that if you take so of course the thing that's really generated by its free bosons is usually called the Kac-Moody algebra. But the Kac-Moody algebra in any sort of either it's terrible or it's also terrible in quotient by some kind of. I mean, I think a lot of people here don't find it terrible. I think a lot of people in this room really love Kac-Moody algebra. So but you know, if you're at an integer level, then you can kind of have a nice rational quotient, well, nice sort of some nice quotient of it, and that's what I call the WZW algebra. And now you could ask, what are the simple current extensions of that WZW algebra? And something that I think was, I'll just write it over here. So I think I think the theorem in this version is due to, let's see, so I think maybe it was Fuchs who shows that the in any WZW algebra, the simple currents are just the center of the group for any Lie group as a group. So this is some group. These are like the abelian anions for your theory. And this is false. This is in any WZW algebra which does not contain E8 at level 2. And now it's a true theorem. And so, and then I think Enrique explains that sort of checks that when you can actually do a simple current extension. And so you could sort of talk about non-simply connected, but not simply connected WZW algebras, but not simply connected WZW algebras. These are the same. These are simple current extensions of the WZW algebra of WZW algebra G at level K. And what he checks is that the levels, the sort of cohomology all works out. So you would expect to have one of these exactly when. So what would you expect? You'd expect to sort of, you could look at the quotient G by some subgroup of its center. That would be like some other form of G, some non-simply connected form. And you'd expect to have a classification of WZW algebras for this given by like the cohomology of this group, or of the classified space of this group. And indeed, that matches the sort of when you can do a simple current extension. So anyway, so that this quickly gets me in the sort of, this is sort of starting to be how it sort of immediately gets me off the ground in the theorem, because whatever V is, it has to be a Z2 extension of V even. And so I can quickly get down to a world of just sort of groups with a Z2 element in their center and start working from there. And there has to be a Z2 element of a specific spin, well, of spin 3 halves, because I don't have any free fermions, but I have to have a superconformal generator spin 3 halves. So you quickly get down to a short list of possible groups that you can check to do this type of thing. So what's really going on in my theorem? I've used half my time. No, I've used 3/5 of my time. So what's really going on in this theorem is the following. So I said that I was sort of talking about sporadic groups, and the point is that that Conway's group, in addition to having this beautiful description, also lots of sporadic groups live in. So lots of sporadic groups. So as I said, Conway's group itself is this beautifully, particularly elegant object. But lots of sporadic groups, you can find them inside of Conway's group by doing some sort of relatively straightforward thing, it turns out. Or maybe not just sporadic, but maybe I should say sort of exceptional groups. So the word that sporadic means something precise in group theory. The word exceptional isn't a precise thing. It just means it's exceptional. Like it means it has some behavior that's not part of the sort of systematic behavior of all groups. So a lot of exceptional groups live inside of Conway's group, and an example, which is why I did my theorem, is I think it's due to Thompson. So he calls it the Suzuki chain, which if you try to Google, you get stuck because it just gives you like things that go around hires. You have to, so I've done that like about all the time. So what he does is the following. So inside of Conway's group, you can find you can look inside of Conway 1, and inside of it you can find a large alternating group. The largest alternating group you can fit inside of Conway 1 is an alternating group on 9 things. And then what you can do is you can pick some, say, interesting subgroups of a 9. So for instance, you pick, for instance, AM, where m plus 1, where m is less than 8. You really shouldn't think of A9 as a thing on 9 things, because of course the smallest representation of A9 is 8 dimensions. So this is really a sort of 8-dimensional object. And Conway, I told you, was like living on the Leech lattice. It's really a 24-dimensional object. So this is living inside of PSO 24, and A9 is living inside of PSO 8. And this is living inside, of course, PSO M. And so you can pick some sort of subgroup like AM, M plus 1, and then what you can do is you can work out the normalizer of AM plus 1, and maybe quotient by AM plus 1 itself. And so this gives you some interesting family of groups indexed by M. So this is what Thompson calls the Suzuki chain. And the family you get is, well, let's see. If you took A2 is the trivial group, and the normalizer of the trivial group's everything. So that's Conway 1 itself. And then the next thing you get is the Suzuki group, which is why he calls it the Suzuki group. Colon just means semi-direct product in group theory, and 2 just means Z mod 2 in group theory. And the next one you get is G2, the sort of F4 points of G2. And the next one you get is the Yanko's second group. I mentioned Yanko already. And the next one you get is the F3 points of the unitary group. And then you get some other crap. So this is, let's say, 2, 3, 4, 5, 6. The next one you get is the sort of L2, 7, and then you get an A4, and then you get an A3, and that's about as far as you go. So this A3 just means, as I said, this is like an 8-dimensional thing. So you can really stick three 8s inside of 24, and this A3 just produces. And then a few other things you could do. For instance, you could like stick inside, say, A4 by A4. Oh, I should have just written them over here. I have my whole list. So this was, so let's see, this was A6. This came from A5. This came from A4. Here was A3. And this was sort of the silly one, A2. And the other things you could do is you could stick like an A4 times A4 in. That fits inside of A8. And when you look at the normalizer of an A4 times A4 inside of A8, you get the normalizer is U43 by D8. And this is really exceptional because it's very rare for Lie groups to have such a large outer automorphism group as D8. This is like the semi-direct product of this Lie group, which you wouldn't expect to have very many automorphisms, and then this ginormous automorphism. And then let's see what else you could do. You could put an A3 by A3 by A3 in, for instance, since that fits inside of A9, and that gives you the kind of M equals 8 case of this sequence. And of course, 8 is a magic number. So that is starting to show you where these groups come from. But now, where do they really come from? So what they're really doing is the following. So I said I could stick this in here inside of here, but I sort of lied to you slightly. I mean, it's true what I wrote, but see, when you think of Conway living inside of PSO 24 versus thinking of A9 living inside of PSO 8, you might have thought I was writing 24 as 8 copies of the vector representation of PSO 8, but I'm not. I'm writing this as 24 is 3 copies of the positive spinor representation, the positive half spin representation of spin 8. I mean, of course, this is like, I really should take double covers of all of these and look in sort of Schur covers of all of these and look inside the Schur covers, the simply connected covers. And now I have actual representation. So this is all I want to say is this is really like this right here. You see some triality going on when you follow this around, and that tells you that if you look at these subgroups, you're actually seeing spin representations. So let me remind you what the spin groups look like. So in low dimension. So right. So what am I doing? So really that means that I shouldn't. So like. Yeah, so for example, I mean, so like, what's a good example? So you know that kind of if you think of, say, something like spin 6 inside of, or I don't know, SO6, whatever you want to call it, inside of PSO 8, but if you sort of make this act on the spinor representation and restrict the representation, then you get the spinor representation here. And in terms of the spinor representation of PSO 6, I don't know why I read that twice. Of course, PSO 6 is really like PSU. SU4. I mean, it's really about kind of other interesting groups and acting on its 4D, on its standard representation. And all the small ones except for 7 have all the small spin groups have sort of interesting coincidences. So I've already mentioned the triality automorphism of SO8 that says that SO8 is isomorphic to SO8 in an interesting way that exchanges the spinor and vector representations, and all the other ones do too. So you have things like spin 5 is SP is the symplectic group of rank 2. So this is the thing that acts on kind of two-dimensional quaternion X space, for instance. So now what I want to do is the following. So these two families are just infinite families in my classification. So you can work those out somehow systematically, that these each have a unique n equals 1 sort of extension. And now what I can do is the following. I can take, what I want to do is I want to take, so I have some favored extensions. So like I look at sort of spin. So let me just restore some. So of course, this was 3 copies in. So if I restored central charges, if I restored, not central charges, if I restored WZW levels, then I'd be looking at like spin 24 at level 1. And I could look at, say, spin M at level 3 and embed in. That would be a WZW, like just sort of the levels go right. This is like you just take 3 copies of the spin representation of spin M and stick them inside of 24 for n less than 8 or something like that. And then I told you this guy has a favorite supersymmetric extension, a unique supersymmetric extension without fermions. And this one has a unique supersymmetric extension without fermions. And now what I want you to do is you sort of, then you work a little bit. It's not that bad, but you work a little and you extend this to sort of an inclusion of inclusion of n equals 1 algebras of n equals 1 theories. And well, anytime you have an inclusion of vertex algebras, we saw this in the sort of morning talks. Anytime you have an inclusion of vertex algebras, it has a corresponding coset model. So there's a coset algebra, coset. How do you write that? But these are all like really nice. You can sort of work out what all of these are, and they all come from an interesting thing. Like in here was PSU4 with its vector representation. And the coset of PSU4 with its vector representation inside of a big, it doesn't matter what value 4 is. The coset of, like, if you take like an SU group with its vector representation and take its coset and size of spin group up to some silly simple current extensions, you get the kind of level rank dual algebra. So these cosets are all just sort of easy things. They're all kind of level rank duals. These all turn out to be kind of level rank duals to the sort of interesting, so the things that you got from sort of from exceptional isomorphisms of spin groups to well, what are they? Okay, maybe I should just write the full list out. Well, I can just point them to you. So, well, that's how they all come up. That's how they almost all come up. So what is the list of spin groups? It's like, well, I told you 2 of them. So it's like, for instance, here I'd have something like SP5 at level 3. So spin 5 at level 3, which is actually SP2 at level 3, and acting inside of acting on H2. And if you take kind of the level rank dual of spin 2 at level 3 is, of course, spin 3 at level 2. Sorry, not spin, SP3 at level 2. And so that after the cosets, you get that. And then, well, you need to make sure that you get so there's sort of 2 things you have to do. You have to make sure that you can embed this at the level, these are some extensions. It might have gone wrong that my extension even embedded at all, because I had to pick some extension of the even parts. But that doesn't go wrong. And then the other thing you have to do is make sure that you can get a supersymmetry on the other side. And well, how does cosets work? So of course, the cosets are just all the things all those fields that commute with the other side. And as I'm sure everybody knows, if you have some inclusion sort of algebras A and B, and you look at the coset kind of whatever B on A, then the rule goes that so this is just of course the things, the centralizer of A, and the standard rule for the conformal vectors is that if this had conformal vector, I don't know, nu B, and this has conformal vector nu A, then this has conformal vector nu B minus nu A is the conformal vector. And the same thing works for n equals 1 algebras. So maybe I should say that if these are both n equals 1 VOAs, so let's say a map of VOAs A into B such that both are n equals 1. I'll call this map is let's call it a supersymmetric map. Is Suzy. If let's call this map, let's say, like, what is the homomorphism of n equals 1 VOAs? It should be one where you can take a coset and still get an n equals 1 VOA. So you could take like the conformal vector in the big guy, you could subtract off the conformal vector in the subgroup, and you could ask that this lives in the coset. Particularly good request. It doesn't happen automatically if I just had a VOA map, because maybe that just didn't do anything nice to the conformal vectors. That's extra choice. But if it does, then of course, then it is a superconformal vector. So for the coset. So that's how you build most of the entries on this list. And then once you have this good, strong control, you somehow, so on the one hand, like I know, so how do I build most of the entries on the list? Like I know where the, I know what it should be, and this lets me sort of control the, like, sort of see why there should be a superconformal vector and lets me guess what the automorphism group should be. Because like, oh, and the automorphism group, kind of my guess for the automorphism group should be just whatever this normalizer mod center is on the other side. But you think of sort of, well, okay, of course, normalizers are just some extension, like, you know, it's morally true. It's not really true, but it's like, you know, morally, I mean, this is the type of, okay, it's not even true at all. It's not even morally true, but it's almost true that that the normalizer of some group, like, should be something like the product. Like every extension is something like a product. I mean, except it isn't, but of course it should be something like a product. You would sort of want it to be a product, and this guy lives inside of Conway's group, and so you should think that this is the thing. Well, this is the person who acts on the but this guy acts on the sort of spin. So this lives inside of Conway's group, which acts on which is the symmetries of the supersymmetric extension of spin 24, 1. This guy acts on spin n, 3 and or n a level 3, and so you expect and in fact get that this guy, that the corresponding dual group should act on the kind of the level rank dual. So that's what you expect, and that you can see that it couldn't be anything bigger, and then you do a character table calculation to see that there's a unique superconformal vector with that automorphism group, and that's basically how you do the classification. So so that finished the classification. So that's sort of how the classification works, is it's really kind of about just reaching inside of my favorite object and looking at kind of coset pairs. And I want to finish. I have like, what, I have 2 minutes left? So 3 minutes left. Okay, so let me just finish by sort of saying some other things. So that's how most, well, it's how exactly the ones I listed come up. So it's how like this one and this one and this one, all how you build all of those supersymmetric field theories. Now, every once in a while, so what's going on with these other ones? So what's going on with these other ones is that, for instance, these two algebras, they're both subalgebras of spin 24, but they're actually a conformal embedding. So you know, what's the central charge of spin 12 at level 1? It's just like 12 halves. So this is like spin, 24 halves. Is its central charge? This is 24 halves. Is its central charge? This is 24 halves. 8 and 16 is 24. So these subalgebras are conformal embeddings. And what can happen, what can go wrong, is that sort of. So what can go wrong? Maybe I can finally use this board. I finished the thing. Oh, and the reason why C condition here is just because I couldn't do that case. So that's why it's there. I'm erasing it, but like if anyone wants to try, like I don't think that E8 at level 2 and E7 at level 2 have superconformal extensions. I know of like 3 superconformal extensions of E7 at level 1 squared, but I don't know if they're isomorphic or not. And I don't know any of their automorphism groups. So it'd be great to like finish this, like rule out those cases. The E8 at level 2 one is just the following question. You take the Grace algebra for E8 and you ask, does it have an element of non-zero norm that squares to 0? And that's just this question. It's just some like question about representation theory of E8, and I can't do it. So what can go wrong is that well, sort of often in examples, and you might get used to often in examples. If you just sort of any algebra, like if you have sort of A and the B, and you compute the coset B over A, and then you compute the double coset. I mean, this is a terrible name. We shouldn't have ever called these cosets because the word double coset means something else, but I don't have a better name for it. But I mean, you do the double commutator, kind of B on B over A, and that of course contains A. And often in examples, this is an iso. This is an iso. So I mean, there's no reason for the double commutator to be isomorphic to original algebra, but often is. And sometimes there's a reason. Like sometimes you could prove it is, but sometimes isn't. Like it isn't. So it is an iso in these level rank duality cases, but it's not an iso for example, if this was a conformal embedding. Is a conformal embedding, like if they have the same central charge. Because then the coset's just the trivial algebra. And the double coset's all of B and not back to A. And so, but when this happens, so if you're in the case, for instance, of a conformal embedding, so in the case of a conformal embedding, there's another thing that might be called that's sort of also a commutator. So in the kind of conformal embedding case, so an example where what's an example of a conformal embedding? An example of a conformal embedding is just like the fixed points for some finite group action, for example. And in the conformal embedding case, at least with everybody rational, in the conformal embedding case with everybody rational, there is a coset. It's always true that if you have a conformal embedding A into B, A is always the fixed points, not necessarily of a group acting on it, but of some fusion category. And I think Andrew told us yesterday that fusion categories act on lots of things. This is one of the things that fusion categories can act on, is on vertex algebras. And you can just recover the fusion category from the embedding. So you might think of the fusion category as being like the commutator of the algebra. So C is also morally a different morally. I mean, this is also a commutator. It's like a different commutator. That's because the other commutator was the wrong commutator. It didn't do what you wanted it to do. And you always, at least in the rational case, you always get a perfect correspondence for these guys. And so anyway, that's how you handle these other cases. Like this guy corresponds to an action of SU2 at level 1 acting on, I think I should have written this in red. This guy corresponds to like the fusion category, not like, I don't mean that it's a coset of an SU2 level 1. I mean, you take the fusion category SU2 level 1. That's just a Z2 category with some non-trivial associator. But that guy acts on this theory in an interesting way. And you take its kind of fixed points, which is, again, it's just a Z2. So it's just a Z2 fixed point. And you get this algebra. And this one corresponds to SU2 at level 2 action. So that's like an Ising category acting on Conway. And the same things, these other ones have lower central charge, but they're like, you do a mix of kind of cosets and fusion category actions to build all of them. And it's not very bad. It's all kind of finite group theory, really, because like this is an Ising category. It's not really a group, but an Ising category is basically a Z2 extension of Z2. So I'm over time. Can I have 1 minute, 2 minutes, 1 minute more? Okay. So the last thing, let me just end by just putting let me use this as an excuse to make a question that I want to know the answer to. I don't know if anyone else wants to know the answer to, so it's not like a big open question. As I said, this talk but here's a question that I kind of, maybe I should say it as a conjecture. So when I did this theorem because I cared, what did I want to do? I wanted to know where do these Suzuki chain groups come from the perspective of VOA theory. And it was an interesting question because the Suzuki chain groups are some interesting family of subgroups of Conway's group. So there's other interesting families of subgroups of Conway's group. So Conway's group has lots we really understand the subgroups of Conway's group really well because we have all of lattice theory, all of Leach theory to use to get them. So there's another interesting family beside Conway 1 are called I won't explain what they are, but they're called the umbral groups. Well, I mean, I actually did earlier, but they're the outer automorphism groups of Niemeyer lattices. And my conjecture that I want to just sort of mention, because I don't know a clue how to do it, is that that the simple, okay, I didn't give it a name. Anyway, that there's an action that for every Niemeyer lattice. So a Niemeyer lattice is some rank 24 lattice, and Niemeyer lattices have something called a Coxeter number, which you compute just like the Coxeter number for a Lie group. So for every Niemeyer lattice, there should be an action on the spin 24 1 plus fermions. An action on this n equals 1 SVOA by the umbral group should commute with an action by another of these. So the umbral groups, you can find some big umbral groups inside of these, which is part of why you might believe me. The umbral group times the fusion category SU2 at level H-2, where H is the Coxeter number of the Niemeyer lattice. And I'll just end here because the problem, well, I won't finish the sentence. So the problem is that the first few SU2 at level n's are this is just a Z2, this is just an Ising category, which is an extension Z2 by Z2. But the next one is a Z2 times Fibonacci. And I have no idea how to tell when Fibonacci can act on a given vertex algebra. I don't know. I mean, I don't know how anybody can tell it. I think there's just this big question, which is, we're really good at working out when finite groups can act on things. That's called representation theory. But for vertex algebra theory, we'd like to know, I'd like to know, how do you tell whether this fusion category acts on this thing and classify all the ways to do it? And I don't know any techniques at all unless the fusion category is secretly finite groups. So any insight at all on this would be great, even for the next one. So I stop here.
Any questions for our speaker?
Is there a connection to equivariant TMF? And I guess there are two questions because you can put it on both sides of 0, 1. So.
Great. So for the story for 100% of my talk, the answer is no. I don't know of any connections between this story and anything about CMF. The reason I want to know this is because exactly about some CMF conjecture. So now I'm just going to talk to Sergey, and all the rest of you won't understand what I'm saying. So if I did have an action by this fusion category on this object, then I could take the n equals 1 WZW algebra for this with this labeling, stack it with this object purely anti-holomorphic. So that was the 0, 1 algebra, and think of this anti-holomorphic. Gauge this fusion category symmetry. Now it acts sort of diagonally the fusion category acts first by Virasoro lines on the WZW algebra, and then by whatever my action is here. And those diagonal actions the anomalies cancel, so you can gauge the whole thing. So that gives me some interesting n equals 0, 1 full conformal field theory. And I've built it, well, if I could do this conjecture, it builds with an action by umbral group. And now I could ask, does that interesting theory, it might have a bigger action than umbral group, but it certainly has an action by umbral group. So now I could look, so that'll have anomaly 27, because I get a 24th report, sort of, it'll have gravitational anomaly 27, 24 plus 3. And now I could look for, so that's like a kind of homology degree, and I could look for choices of bounding. I could look for a sort of way to co-bound this theory. So a way to deform the theory to one with supersymmetry spontaneously breaking. So that deformation would be like a thing with anomaly 24 plus 4. And what we explained with Davide is that when you have this type of kind of thing that bounds theory of dimension sort of 3 mod 24, then you can extract Mach modular forms from that data. And so what I'd like is that this would be a way to build the Mach modular forms, like to sort of justify the role of Mach modular. But since I can't even solve this problem, I can't start trying to find whether it's bounding or not.
Let's take one more question from Chris.
Yeah, it's kind of a basic questions. So you have this kind of precise association between these super VOAs and their automorphism groups. I mean, was it clear beforehand that the automorphism groups should kind of correspond precisely to this
No.
extension? Okay.
I mean, there's Igor Frankl has a dream. And in Igor's dream, I mean, Igor knows this isn't true, but like it's a sort of nice fantasy. And in Igor's dream, every Lie group has a vertex algebra that's its favorite vertex algebra. Well, every Lie group has a favorite representation called the adjoint representation. And why Lie theory is relatively easy is because you have these good linear objects that every Lie group acts on. And Igor's dream would be that every finite group should have a nice linear object on which it would act. Now, this isn't true because some finite groups just don't have small linear representations. I mean, most of them do, but this kind of what are called the monster sections, the top generation of sporadic groups, do not have small linear representations. So I should say, like, the monster group isn't very big from the perspective of finite group theory. We have this idea that, oh, it's as many particles as there are particles in Jupiter or something like that, but that's actually pretty small. Like monster group is smaller than the, like, a symmetric group on 24 elements. Monster group is smaller than the like F2 points of E8 or something like that. Like monster groups are just not very big from the perspective of finite group theory. What makes monster group really big is that its smallest linear representation is 200,000 dimensional. But on the other hand, monster group has a nice small base, essentially linear representation on the monster vertex algebra. And so Igor's dream is that this should be how every finite group should work. And this should be how the classification of finite groups works, is you should go in and, like, for every finite group, associate a vertex algebra representation, which you think of as being like the adjoint representation. I don't know if, that dream's probably just wrong. And it's probably not correct that these are the right representations in any sort of there's just probably more than one thing that a given finite group acts on.
Okay. Thanks, everybody. Let's thank Theo again.